Okay. All right, so this example is available to you in the Unit 6 examples that I posted. So this is a problem out of Chapter 17, and this is a double slit problem. Okay, so here, I'll read what the problem says. All right, it says, light from a sodium lamp with a wavelength of 589 nanometers illuminates two narrow slits. The fringe spacing on the screen, 150 centimeters behind the slits, is 4 millimeters. What is the spacing between the slits? Okay, so they told me the wavelength of my lamp, which was 589 nanometers, which I immediately convert to meters. The screen is 150 centimeters away, so this distance right here is 150 centimeters, or 1.5 meters. And then it says the spacing is 4 millimeters. So that means the spacing between the central maximum and the first slit is 4, or the first slit in the second, or the first bright fringe and the second bright fringe is 4, and so on. So they told me what this distance right here was. What they want me to find is D, the distance between the slits. Okay, now, the double slit formula is given here. Remember I said that path length difference was D sine theta. That has to be equal to a whole number multiple m times the wavelength. So m can be any integer. It can be 0, 1, 2, 3, 4, and so on. So D sine theta equals m lambda is for constructive interference for a double slit. All right, so I'm just picking the first one because that's easy. So I know that the order number for the slit, or the order number for the fringe, is whatever maximum is. It says, if it says the first maximum, the m is 1. If it says the second maximum, m is 2. The central maximum would be m is 0 because it's straight across. Okay, so 0, 1, 2, 3 is how it goes. Okay, so that's the first thing. Now, the next thing I have to do is I have to ask myself, is the distance the screen away, is it much larger than how far apart the fringes are? And in this case, the answer to that question is yes, because the screen is 1.5 meters away and the spacing between the fringes is 0.004 meters. So that counts as much bigger. So what that means is I've got a long, skinny triangle. And for a long, skinny triangle, you can use something called the small angle approximation, which you may have seen in a trig class. But basically what that says is for a long, skinny right triangle, this long side here is essentially the same length as the hypotenuse. So I can replace the sine of this angle, theta, which is opposite over hypotenuse, with the tangent of this angle, theta, which would be this angle here, and I failed to draw it on there, I apologize, but it's this little angle here that was in the previous picture. The tangent of that angle is opposite over adjacent. So sine is opposite, which is y, over the hypotenuse. Tangent is opposite over adjacent. Since I can replace that, I can say that the thing I really want to know instead of sine theta is tangent, and the tangent is y over L. So the small angle approximation means that you can replace sine with the spacing between the fringes divided by the distance to the screen. And that's only good if y is little bitty compared to L, okay? And usually it'll say in there that the screen is much, much farther away, or that the spacing is small compared to the screen distance, or it'll even say just use the small angle approximation. So I can replace sine theta with y over L, so I end up with this equation here. D times y over L is equal to m lambda. I'm using the first order, so m is 1. So I simply just plug in my numbers. I know I'm looking for D, which is the slit spacing. I know y, I know L, I know m, and I know the wavelength. So I just solve for D. Fairly straightforward. And that's about as difficult as those problems get. I mean, you have to know enough to be able to solve for all the parts. Okay? Any questions about that? Okay? All right. So let me get out of this.